Hello guys, welcome on Tesla Adventures. In this video today we are going to discuss the Bernoulli's theorem and its proof and what is the significance and what is the real meaning of Bernoulli's theorem. But to study the Bernoulli's theorem we need to understand the pressure energy. So to understand the pressure energy, let us suppose that there is a container which is containing some liquid. The height of the liquid filled in the container is h, and there is a pipe which can let this liquid out of the container. But this liquid is being stopped by this piston which is not allowing the liquid to flow out of the container. And there is some external force which is applied by me. I am the external agent. So there is some external force applied by the external agent, and this force is pushing this liquid inside the container. Now let us suppose that by applying this external force we are pushing the liquid by a small distance dx inside the container, and for this we have to apply this force. Now we are pushing this piston very slowly. So this is very important, that piston is being pushed very slowly, which means that the net force acting on the piston will be 0. Now let us suppose that we have displaced the piston by a distance of dx inside the container, and obviously the pressure at this point, let's suppose it is A and let's suppose it is B. So pressure at A will be equal to P naught plus H rho G, and pressure at B will be equal to pressure at A because they are at same level, and pressure at B will be equal to P naught plus H rho G, and this will be equal to the external pressure, which is F external upon area of the piston, plus P naught. Now P naught will be cancelled out and F external will be equal to H rho G A. So this external force is required to move this piston slowly inside the container. Now the work done by this external force will be equal to F external into dx, and this work done will be called as pressure. Now you know that if as an external agent I have done some work on the liquid against the pressure of the liquid, so this work done will be stored inside the liquid in form of pressure energy. But pressure energy is nothing else but it is the potential energy of the liquid. See, you can see that if I'll push this liquid inside the container, then this level of liquid will go up, and hence we can say that the potential energy of the liquid filled in the container will slightly increase. So the change in potential energy will be the pressure energy, or we can say that this is pressure energy, and this pressure energy is equal to F external, which is H rho G A into dx. Now A dx is the volume, so this pressure energy per unit volume dV is called as H rho G, and it is numerically equal to the pressure. So first of all, very important thing is the fact that pressure energy density, this is pressure energy density. So pressure energy density is numerically equal to the pressure. This is the important thing. And actually the pressure energy density is the increase in potential energy of the liquid by per unit volume when we are doing some work on the liquid. Now let us move on the Bernoulli's theorem. Now Bernoulli's theorem is actually the law of conservation of energy. So I'll tell you how. So consider a long pipe whose some part is shown in the figure. This is not an isolated pipe. Let me tell you, this is a long pipe whose this partial part is shown in this figure. So there is some liquid which is pushing this liquid inside this pipe, and there is some liquid in the front of this section which is pushing this inside this pipe. But liquid is flowing like this, and we are concentrating on this section only. So this is only a section of a long pipe, and there is continuously liquid coming from the other parts of the pipe. Okay, but we are concentrating on this part only. So let us suppose that due to the pressure of the liquid, this liquid is pushed inside by a distance of dx1, and this is pushed outside by a distance of dx2. And let us suppose that the pressure at this end is P1. So we can say that the liquid behind this pipe in this region is pushing this liquid inside the pipe. So the work done will be P1 into area is A1 and displacement is dx1. P1 into area is the force and dx is the displacement. Now as this liquid will move out, this liquid which is in front of this pipe here would stop this liquid to come out, and hence the work done by this liquid on the pipe will be negative. So it would be minus P2 into A2 into dx2. This is the net work done by the external liquid on this section of pipe. Now this work done will be stored in the form of potential energy, change in potential energy of the liquid of this section, plus change in kinetic energy of the liquid of this section, which is delta K. Now we can write down this is P1 minus P2 into dV. Now dV A1 dx1 and A2 dx2, A1 dx1 and A2 dx2 will be same, and they will be equal to the volume of the liquid which is pushed inside, because the amount of volume which is pushed inside the pipe will be equal to the amount of volume which is pushed outside the pipe. So dV will be common, and the change in potential energy will be dm into rho into h2 minus h1. I have considered that h2 is greater than h1, and change in kinetic will be half dm into v. This is g. So half dm into v2 square minus v1 square. Again, I have considered that v2 will be greater than v1. I have just assumed this. There is no issue in this assumption. So now we can say that P1 minus P2 will be equal to this is dm by dv, which is rho g h2 minus h1 and plus half rho into v2 square minus v1 square. So P1 plus rho g h1 plus half rho v1 square will be equal to P2 plus rho g h2 plus half rho v2 square. Now this is the general form of Bernoulli's theorem, and we can also write it down as P plus rho gh plus half rho v square is constant, where this P is the pressure energy per unit volume, and this rho gh is potential energy per unit volume. This is potential energy per unit volume, and this is kinetic energy per unit volume. Okay, so this is the Bernoulli's theorem, which says that the sum of pressure energy per unit volume, potential energy per unit volume, and kinetic energy per unit volume in a flowing ideal fluid remains constant throughout the pipe. Now, if we divide this complete equation by rho g, so it would be P by rho g plus h plus half into v square by g. So this is another form of Bernoulli, and this is called as pressure head. This is pressure head. This is potential head. Potential head. And this term, this is constant. And this term is called as kinetic head. This is kinetic head. Okay, and if we apply some external force on the liquid, then the Bernoulli's theorem will be the sum of work done by the external force per unit volume plus pressure energy per unit volume plus kinetic energy per unit volume plus potential energy per unit volume of ideal flowing liquid will be constant. And if we treat the gas as a liquid, then we can say that the Bernoulli's theorem says that the sum of pressure energy per unit volume, kinetic energy per unit volume, potential energy per unit volume, and the internal energy per unit volume of the gas will remain constant. In this case, we have to consider the internal energy of the gas also. And in the case of some external force, we have to consider the work done by that external force per unit volume in the in the equation of Bernoulli's theorem. So guys, this was that complete derivation and the concepts of Bernoulli's theorem. And in the next video, we will be bringing the world famous concept, world famous application of Bernoulli's theorem, which is the Magnus effect. So we'll be bringing the Magnus effect, and I'll be explaining the Magnus effect with high detail. Thank you.